Yeah, so we have a very special guest today, Nick from Demandbase. He's going to talk about analytics at Demandbase, how they do customer-facing analytics. So first, he's gonna do a presentation, and then we're gonna do a short discussion, and then we're gonna have time to handle everybody's questions, right? So now let's get started. I'll hand everything to you first, Nick.
All right, great. Thank you so much, Sida. Thank you, everyone, for joining today. Yeah, so just a little bit about me. Principal software engineer here at Demandbase. I've been at Demandbase for about 3.5 years now. And in my career, I've primarily worked on data platform teams at software as a service companies with a real focus on data-intensive applications, database systems, and because of that, a lot of data migration projects like the one that we're going to be talking about today. So what we're going to talk about, going to talk a little bit about a little brief introduction about Demandbase and this project that we've been doing around analytics, the challenges that we face with ClickHouse, little discussion about denormalization versus normalization in the world of analytics queries, and then some information about the migration that we did to CelerData. So real quickly about Demandbase. What is Demandbase? We're a leading business-to-business account-based go-to-market platform. So what is account-based marketing? Basically, it's the idea that when a business is selling to another business, you might not be selling to a whole company, but maybe a division or a physical location of that company. And so that's the account. A person is too small, a company is too big. So we create this idea of an account that you market to. And Demandbase integrates all of your sales, marketing, and ads data together in this single platform to let you make use of all of your data so that you can use your marketing budget to its best ability, reaching out to the right people at the right companies at the right time. So in the world of analytics, our main application, Demandbase One, provides this powerful platform for our customers to explore and analyze all of their marketing and sales data. This application supports more than 50 reports that we've designed, and that number is growing all the time. And in those reports, customers can use data from integrations that they bring in, including custom fields that they've imported from those integrations. And then we provide a high degree of customization of those reports to our customers, whether it's the data that they're pulling from those reports or the filtering that they're doing. We have a very complex rules engine that allows for our customers to really filter their data to exactly what they want. And so all of this configurability means that each one of our customers is very unique in their analytics needs, both in the size and shape of their data and the types of queries that they're running, even if it is a pre-canned report in some respects. So these reports that we're doing, they're live in the UI, and so doing live analytics means our queries need to be fast, right? Nobody wants to open a web page to get a report, walk off to get a cup of coffee, come back and hope that the page is finally loaded. So we need to be reasonably responsive. But because of we face greater challenges because of all that customizability. We have a lot of semi-structured data that we store in JSON for our customers, and JSON is inherently more difficult to query. And so for this initial implementation of this analytics system, we chose ClickHouse and got to the point where we had about a petabyte of denormalized data stored across 40 ClickHouse clusters. So we face a number of challenges with our work with ClickHouse. I'm going to go through those now. So what was some of the limitations with our ClickHouse-based architecture? So, ClickHouse is famous for being really good at processing denormalized data, but it is, generally has very poor join query performance. And so denormalization was a must. But we have a lot of one-to-many interaction between tables in our data. And so we had a large explosion in the size of our data when we denormalized it. And loading this data into ClickHouse could take hours. And in fact, reloading an entire ClickHouse cluster could take up to a week just because of the load of data. And then we just had numerous challenges at scale supporting all of those different clusters. And at the end, we still struggled with query performance, especially for our larger customers. There were always a few reports that were always struggling, and where we were always trying to tweak things to make things work better for those customers. So what made our data explode in size when we denormalized it? So let's take a look at some of our data. So we have three main tables that are the core, really core of our data. In the normalized view, we have events. So these could be viewing a web page, downloading a white paper, or going to a webinar. People, self-explanatory. These are the people that these events are about. And then the account is that account-based marketing concept, that company that person belongs to. And so by data size, the events are very small. The people are fairly large, and the accounts are the largest objects per row. But then when we look at the number of actual records, we have very few accounts. More persons makes sense. You'd have several people at any given account or company. But then we have a very large number of events. And so denormalizing these things together means that we're duplicating these person and these account objects, tens, hundreds of times. But those are our largest data records. And so that's what leads to an explosion of data for us and probably many other people doing these kinds of denormalization. So what was the cost of all this denormalization? So it ended up that we were paying more for disk than compute with our ClickHouse clusters. We've calculated that even in a columnar optimized data store, the denormalized data was at least 10 times larger than it was normalized. And in addition to just paying for a lot of disk, we were also needing to pay for the highest performance drives from AWS, to get the highest throughput, the highest IOPS in order to meet our performance targets. But even with all of this denormalization work, we still had queries that required joins. In fact, most of our queries still had joins. We have concept of membership lists of accounts or persons, and most of the queries that our customers run use one of those lists as a filter, and so we were always joining in that part of that table as a filter in a large number of our queries. And then we had issues with the computation of this denormalized data. The cost of our ETL process of taking the normalized data, doing computation, and then denormalizing it together meant that we could really only run this about once a day. And in fact, for older event data, we usually had to do it only a few times a week, or maybe even only once a week, in order to have reasonable costs, and also to be able to just be able to load the data into ClickHouse. Even with the amount of dedicated write resources we gave ClickHouse to do this. And then every time we changed the schema of this denormalized view of the data, adding a column, well, you had to recompute all of this denormalized data again to add that column to it. So it could take a week or more before that data got into the system for all customers. And so there was a real lag time between trying to add something and it showing up in the product. And then on the performance issues, JSON has always been one of the challenges for us at Demandbase. Again, we have a lot of these big objects. Some of them are quite large, especially some of the custom data our customers bring in. And we found that we really couldn't use the JSON field type in ClickHouse. We had struggles with it. So we stored the JSON as a string, and we would parse it at query time. So we were parsing this parsing this JSON at query time. So that takes effort. And then this denormalization meant that if we're pulling something from those accounts or persons off of an event from the JSON, we're spending a lot of our CPU resources parsing that JSON. Or even more so in the case where we're filtering on something from that JSON. Now you're having to, read that JSON from every single object for every single event. And so this could lead to, a number of complaints that were just, always kind of occurring in the background of various query latencies or struggles from some of our customers. And then there was the efforts of maintaining all of these clusters. And so we faced this constant challenge of, our customers would onboard new data. They would, their needs would change and grow. And we'd find that we'd constantly need to migrate customers out of an overutilized cluster to a new one. But the things I mentioned about how long it took us to load this huge denormalized data meant that there was a long lead time to moving these customers. So we really had to be, several days ahead of there being any problems and beginning that move so that they would be moved off before, the problem became more acute. And so we were, trying to always be bin packing these customers together, which would either lead to over-utilization, low resource utilization, and all of this effort and maintenance that was required was almost a full-time job for a single, employee here at Demandbase. So that's when we started looking at StarRocks and specifically the CelerData Cloud offering. So a little bit about CelerData Cloud, BYOC, bring your own cloud, based off of open source StarRocks, and it's a managed StarRocks that runs in our VPC, and this was something that was really valuable to us. It's a managed service, so a lot of that effort is taken off of us, but the data lives in our AWS accounts. It doesn't leave those accounts. And so that from a security perspective and data security, that was really important and valuable to us. And then the CelerData Cloud supports a number of enterprise access control features, especially row masking policies that we've used quite a bit in our efforts. And then because it uses StarRocks, it's designed for joins on the fly to be really part of its internal DNA. And it has strong ability to scale both horizontally and vertically as our needs change. So just a quick look at the StarRocks cluster architecture. So we went from having 40 ClickHouse clusters to trying to do this in just a single cluster of shared CelerData resources. That cluster has a small number of these FE nodes. Those handle the client connections, query planning, those kinds of things. And then a larger number of backend nodes where the actual data is physically stored. And then the compute of those nodes is used to run the queries. And because of this architecture, a query could come in and the resources of multiple BE nodes, really all the nodes that store data that query involved, could be used in executing that query to speed it up. We didn't need any kind of dedicated write resources. Each BE node was responsible for reading and writing data. And so let's compare that to what we were doing in ClickHouse. So in ClickHouse, we had every one of our clusters had 3 nodes. 2 were identical read nodes, read replicas of each other, and then we had a write node. So we had one node. These 3 nodes were all identical. So we had one third of our resources was strictly for writing data, pulling Parquet files from S3 from our Iceberg tables, processing it into the ClickHouse table format, and then loading those into the read nodes. And then each query would go to one of the 2 load balanced read nodes to be processed. And so with that architecture, to speed up a query, the only thing we can really do is, have more resources on that read node, vertically scale that read node. We could handle more queries by having more read nodes, but we couldn't increase the performance of a given query except by scaling vertically because the resources of only one node could be involved. Where with CelerData, we could make use of all the resources of this whole big cluster for every single query, and we had that great horizontal and vertical scaling. Increase the size of the backend nodes vertically, and just add more BE nodes to scale horizontally. So let's talk about like normalization versus denormalization in the world of analytics queries. This has been talked about a lot, and it's been essential tenet of these kind of workloads. And for a long time now, the idea has been denormalize your data. Disk is cheap. This is going to give you better performance. But is that really, still the case? Is that still the best practices? Denormalization comes with a lot of costs, right? If you have one-to-many relationships in those denormalized objects, you're gonna blow up the size of your storage. In our case, more than 10x. And then you're doing this heavy pre-processing to pre-join this data together to create that denormalized view of data, which really hinders your ability to do real-time analytics. If you have this batch process that has to join this stuff together before loading it, real time is just not possible. And then, with that, you have all the expenses of backfilling data, updates, and all that. With normalization, you're going to be storing much less data. You're not duplicating objects. You can have a much simpler pre-processing pipeline if you even have one at all. Schema evolution is more flexible. Adding a column, you don't have to redo that whole denormalized view of data. You just update that one table, and then everything is fine. But you can only get those benefits if the engine that you're using really handles joins well and is meant to handle them on the fly as part of the way that it was designed. And so how does CelerData make those joins faster and make it possible to normalize data and have really good performance? So part of it comes from the distributed join strategies that they spend a lot of time implementing and optimizing. Two of the standard ones that they have: broadcast join, taking a small table and distributing it to all the other nodes, or in cases where the tables are more equal in size, shuffle joining them between it, and all the optimizations they've done about that. And then because you have a larger number of nodes in their distributed system, you can use the resources of a lot of nodes. So in some cases, you can simply use the amount of compute you have to overcome the barrier of the mathematical challenges of joins. And then on top of that, CelerData has a very strong cost-based optimizer in their query planner. And that really makes a lot of this possible. Things like join reordering to decide what's the order of operations within your query to not just how you've written it, but to make sure that the smaller tables are handled in the right way to join them to the larger tables better. And then some key optimizations around filtering of larger joins using join keys, and just all sorts of other optimizations under the hood. And runtime filtering, I think, is a big one. And just to give you an idea of how this works, a standard join, you might be scanning two different tables, one that's large, one that's pretty small. All of that data is read from all the nodes. It gets shuffled across the whole cluster based on the join key. And then that's your join. You'll get some number of rows out at the end, often like a small number of rows. With runtime filtering, what CelerData can do is it can say, okay, this table's small, this table B. So I'm going to read that one first. I'm going to take all the join keys from scanning that table and distribute them to the nodes that are going to be scanning table A, and use that set of keys as a filter on that table scan. So now, instead of that 10,000 rows needing to be a part of that shuffle join, only the 10 rows that match that filter are going to be involved in that shuffle join. And so that's going to greatly improve your performance and the amount of network traffic that you're conducting. Another powerful tool is the concept of colocation joins. So CelerData gives you the ability to specify a common distribution key across multiple tables. And by doing that, that means that on that distribution key, all the data for that key for all of those tables is going to be on the same physical node. So when you use that key as your join key, CelerData can say, okay, we know all the data exists on the same physical node for a given ID. And so we can take this distributed node and actually make it a bunch of local joins on each one of the backend nodes. And this can have really great improvements to network traffic and memory usage. So you can see in this simplified example, I've got two backend nodes and two tables. Both are distributed by the account ID or on both of the tables. And so everything with account ID 1 in the person table and account ID 1 of the account table exists on the same node. And the same thing for backend node 2 with the IDs that it holds. And so all the data for those joins stays local and doesn't have to be distributed across nodes, which can have a really big performance benefits. There are some caveats to colocation, and we ran into some of these with the skew problems. Because you're distributing the data by these columns, if you have a very uneven distribution of those keys, like we've had in some of our tables, that can really result in problematic data skew. So what we found is our person table contains a number of kind of like we call special account foreign keys, and those IDs could make up 10 to 90% of all person rows. So you might end up with a situation where you have this account ID 0, which makes up a huge number of objects in the person table. Meaning that there's way more data on this backend node 1 for the IDs that it contains than this backend node 2 with IDs that are more distributed in size. And so your query would end up getting bottlenecked on this backend node 1, having to process all of this account ID 0 data. And so in some cases, we did have to move away from colocation until we solved that skew problem. So those are some of the interesting, nice things about CelerData. And now I want to talk about, data migrations are always tricky. They're large, they're expensive, they can take a lot of time. And we used a lot of strategies to improve the speed that we created due to our migration and to reach success. So one of these was we pretended our data was still denormalized. So we had all these queries going against ClickHouse, and obviously we would have to rewrite them so that they used StarRocks SQL instead of ClickHouse SQL. But in addition, to make use of this normalization that we were trying to do in CelerData, we would have had to further refine the queries and rewrite them away from this denormalized view of data that they had been structured towards. Well, with CelerData, we were able to simply just define a view that made all these queries think they were still talking to a denormalized set of data. But that view was just joining together those normalized tables that we had created in CelerData. And that allowed us to move much faster and do much less work during our migration. And then leave rewriting those queries and further optimizing them to after the migration was complete. In reverse, we instead were using the denormalized data to load our normalized tables. So all of this data that we were using was stored in Iceberg tables in S3 in that denormalized view. And we were able to reuse that denormalized view to load both ClickHouse and CelerData at the same time. So we didn't have to rewrite any of our data specific to CelerData. We just reused that data to load. Was it a little bit slower to load because it was larger files? Yes, but because we were avoiding reading any of that denormalized columns that were in each of those tables, the loading was still very, very fast and much more performant. And that greatly helped us, again, push some of the effort, post-migration so that we could get to the successful migration first and then optimize some of these systems later. Another thing we made use of is using foreign keys to avoid unnecessary joins. So I talked about how we have these three tables that are part of this denormalized view, but a lot of queries don't necessarily always use all three of those tables. You might have a query that says, I want events for this particular set of people accounts. Maybe it's all the accounts you have for Oracle or something, or for a geographic region. Well, that doesn't involve any of the columns from the person table, but normally you would have to do that join anyway because you don't know if that join is going to filter out data. But we're able to use the foreign key relationships that CelerData allows you to bake into tables to say, that these IDs that we're joining these tables on are foreign key constraints. And so if you don't need any data from this person table, you don't have to do this join because you're not going to filter out any data because those foreign keys are guaranteed to exist in the other tables involved. And so that can be another performance optimization for using denormalized kind of views, but taking the benefits of normalized data without having to do all the rewrites of your system. And then StarRocks engine that CelerData uses gave us a lot of other benefits when we were working with JSON. I mentioned before, ClickHouse, we weren't able to use their native JSON type, but that was not true. With the StarRocks engine, we were able to store it in the JSON type. And so we weren't parsing at runtime. That was already parsed at loading, and so things were faster. And then because of the normalization, we weren't having to do that reading of the denormalized objects JSON on every record. So we were reading way less JSON, and that led to a number of performance improvements to quite a number of our queries, especially those that filtered on JSON. And then we removed some external lookups. So much of this data was loaded in that daily cadence, but there were certain tables we just had to have a faster view of. So this included those list tables, those membership tables. A customer says, "Hey, I created this new list of people I want to market to. Maybe these are my hot leads, or this. I created this new set of only customers that are in the Midwest, and I want to do action upon this." They don't want to wait hours for that list to be available and to start working. So we loaded those tables into Postgres and then had external connections from ClickHouse to Postgres to read that data at query time, which just added more complexity to our systems to manage. With StarRocks, we were able to stream those narrow lookup tables directly in. And this was easy for us because we were already doing some of that work already. So we were already exporting that data from Postgres using a Kafka Connect tool called Debezium, which takes the Postgres wall log events and writes those into Kafka. And that's actually how we were writing a lot of those Iceberg tables, or at least our kind of our bronze data into our Iceberg data lake. And then we were easily able to just hook those Kafka topics to StarRocks's routine load system and keep those tables updated with less than 1 minute latency. And so we were able to get rid of all of that excess, complexity and still get basically the same, real-time updates for those specific tables. And then finally, the secret weapon, that cost-based optimizer I talked about before, using the table statistics to reorder those joins, optimize the query plan, made it so that we didn't have to be rewriting queries, specifying orders for joins, because the StarRocks engine would really figure that out for us and rewrite the queries to be done in a way that was more optimal, meaning that we spent way less time trying to optimize the queries after we had made them, translated them. Now, the quality that the cost-based optimizer can give you is only good as the quality of the stats you have on the tables. We certainly have some challenges around partition data and each of our partitions having very, very different statistics. And we've been working with CelerData on a number of future enhancements to improve the quality of those stats, to make it so that the cost-based optimizer is even more powerful and even more intelligent in the way that it optimizes your queries. So yeah, thank you everyone for joining. I encourage you to check out the CelerData Cloud and join the StarRocks Slack channel if you're interested in learning more about StarRocks and details about it.
Thank you so much, Nick. Thank you for this amazing talk, and really excited to see those transformative results as you had with StarRocks and CelerData. I have a few questions here first. So the first question would be, what are some of the next steps for analytics at Demandbase?
Yeah, so some of the early next steps, kind of were alluded to in the talk. So one of them was, we recognize that Skew problem. We want to move those tables back to colocation. So we're probably days out from solving that problem within our infrastructure and our architecture, so that we can improve the performance of queries through that. Ongoing projects to remove all that denormalization of our data in our lake. So that's going to save us a bunch of money and time in our ETL. And then the next steps are really all about how can we do things in real time, or if not real time, then same day. None of this overnight updates of data. So trying to get our information to our customers as fast as possible, so they can be using the most real up-to-date data to be making their marketing decisions.
Okay, so thank you. So you mentioned about like data freshness and basically real time, right?
Yeah.
But I hear a lot from the users. A lot of them say real time it's often criticized as a false choice. It's as a false requirement, right? With a lot of people claiming that only a few users actually benefit from it, right? So what is your perspective, and what is the case for Demandbase?
I think everyone likes fresher data, and I think there's a couple different layers to the value of fresh data. So as a data engineer, you have to think about how you have multiple pipelines, often running at different times. And if if you're only refreshing data once a day for certain things, well, any other pipelines that depend on that data can only run after that pipeline. They can only, and then that's another delay of that other downstream data being available. So the complexity of explaining to customers why something isn't why things that they know they loaded aren't visible yet, or they're visible in one place and not another is also problematic. And so the faster that you can update data, the less those cracks appear. And then I think there's just certain kinds of data that needs to be faster. I mentioned, that membership in lists. People need to be able to take action and and experiment and try things and see what happens when they change their data. And so we've definitely seen that. Well,
Yeah,
yes,
that
many
makes a lot of
customers,
sense.
can
As
handle it.
a kind
You
of
need
like
to
a
be
customer
faster.
facing like martech, how does like real time actually real time data freshness, impact your competitiveness, like Demandbase as a whole, in the market? I'm curious.
Yeah, I think it's a really way to stand out. Because demand-based people love our product for the customizability, the flexibility. But when you can then make it so that all that customizability and flexibility can be on changes that you're making inside of your business day. So you're not waiting for the next business day to see how something you change will work. That just that speeds up people's process. It allows them to work faster and more efficiently. And so while people don't necessarily need seconds latency, the more that you can decrease the time between a change and it showing up in the platform, the better.
Okay, thank you. So and we talked about like a little bit, we touched a little bit on Apache Iceberg, right?
Yeah.
As the source data, as the data repository for Demandbase. And we have a question actually in the comment section about Iceberg. And for lakehouse architectures like Apache Iceberg are a really hot topic right now, right? So what is your take? Do you think more workloads in the future are going to be viable on the lakehouse architecture, will be going to be migrated to the lakehouse architecture, right? Especially for like those really demanding, like classic data warehouse like function scenarios, like customer facing analytics. So what is your take on that?
I think there's a lot of things that people are doing today that aren't being using the lakehouse that could use the lakehouse. I think there's still always going to be there's always going to be this need for something even faster. But I think those technologies have really grown in a way that I think that there's going to be a lot more workloads that are going to be able to be powered off of systems like Iceberg in the future.
Yeah, that makes a lot of sense. I mean, that is our vision as well, right? For to run like all sorts of kinds of workloads on like data in open format. I think to store everything in open format, it means that you as a user actually have ownership over the data you have, right? You never get locked in because you own your own data in your own, kind of format, right? And we're definitely working hard to make this, possible for every single user out there as well.
Yeah, and I think that's such an important point about owning your data. You always want the relationship with a vendor to be successful and for and long lived, but you also want to be able to say, well, if something happens, if something changes, we need to be able to still run the business. And it's always good to be able to not feel like you're locked in, that you've
and also like talking,
even if you're never going to need it. Hopefully
exactly.
you don't, but you hope for the best and you plan for the worst.
Yeah, and also with like the ingestion pipeline, right? I think like running off a single source of truth data is just so much better, for data governance, right? And to actually make your data pipeline so much more even simpler, right?
Right, and that's been really a big part of our vision. Yeah, that's been a big part of our vision, that Iceberg as the source of truth where all the data goes to. And then people can access that. Our company can access that data directly from that Iceberg lakehouse, or we can load that into various other other systems like CelerData, or access the Iceberg table through CelerData's external tables. It gives us this huge amount of flexibility in ways that people can access data. It really powers our application.
That makes a lot of sense. Thank you. And my next question would be, for the more junior data engineers that are
Yeah.
just starting out in the big data world, right? What are some of the technologies that they should focus on learning about, like today in late 2024?
Yeah, I think the concept of the lake house, Delta Lake, Apache Iceberg, my personal favorite, and then of course Hootie as well. Those technologies I think are becoming really the core of data storage, in the world of big data today. Of course, you need to get data in and out. So technologies, like Spark and Flink, and Kafka are all rather important. And then, of course, the engines that you're going to use to query that data, things like StarRocks, and all the other engines that are out there. Understanding which ones work for which workloads, and really, finding the ones that meet your needs.
Thank you. And my next question would be, as a kind of like a data engineer veteran, right? You've probably seen systems that probably work fine in the beginning, but falls apart really fast at scale when you're trying to put it into production, right? So what lessons have you learned about designing for scalability?
Yeah, my mantra is model, real is real. Everything looks good on your small test data sets. And so while you need to do those experiments, the most important thing is to get to a full size test as soon as possible. Nothing is going to ever be like your production traffic, your production data, your production workloads. And so getting your system to try that out as early as possible in your process to find all the things that break, I think is the most important aspect of success. Because that way you're not spending a bunch of time designing and building a system that looks good until you put it at production scale and you have to rethink it from the ground up.
Yeah, I totally agree. I mean, yeah, every penny you spend on a POC, it's definitely worth it downstream, right? So you can spot
the
all
bigger
of
a POC you can do, the better. Even if it's just for a short period of time at full scale, do it so that you find all the problems.
Yeah. Thank you. That's all of the questions I have, and let's now take a look at the question from the audience, right? So first question is, what do you use for denormalization? I think Ryan already answered that. All of the ETLs are done using Spark. Anything to add to that?
No, doing all that denormalization in Spark, it works very well, but it's inherently expensive. The amount of data that you are denormalizing and joining together as part of that, just mathematically means that it's costly and it's slow.
Yeah, it makes sense. The next question, for the denormalization part, if rows are sorted properly, Parquet would be able to compress some of the value really well. That's true. Wondering if reorganizing roles can somehow help with the storage costs.
It can always, you can always, do things to make things slightly better. That sorting though is only going to get you benefits for the columns that you're sorting by. If you have wide tables, and we have a lot of wide tables, you're going to have a lot of columns that aren't part of your sort key, and so you may have sorted some of that data, but the rest of that data is going to be randomly distributed. And then that sort would give you the same, you would get that sort benefit on normalized data as well, if not more so. And so you'll actually probably get better compression for normalized data than you would with the denormalized data with something like Parquet.
Yeah, I do agree. I mean, I think even this, this actually both works for, if you're trying to denormalize or you're trying to normalize, right? Columnar just compresses better, right? Yeah. And also, I think for denormalization, it blows up storage in a complete different way, right? You think about like you reduce your storage cost, like going from like something like EBS to like a S3 bucket, right? That's like 90%. That looks like a 10 time, right? But this 10 times is actually going 1 from 10, from 1 to 10. Yeah, that's a huge difference, right? And to sort, sorting, I think you need sorting for many other different things too, right? You sort on the column that you query on, right? And also, you only work on one column, and when you denormalize, the table is incredibly flat. and many
compression only gets you so far, and you have to remember you have to read that data, and so yes, it's compressed on disk, and they'll save you money on disk and on IOPS, but you're still going to read that into memory, and so you're still going to have all that data, and so you still have the problem. You'll balloon up that data in memory, and now you have a problem in memory where you have way less bytes available to you.
Yeah, that makes sense. So our next question. So you used Iceberg as a source of truth and load the data into ClickHouse from Iceberg?
Yes. So yeah, we moved to kind of getting Iceberg as our central unified data platform for teams to load data into, and then that gave us one way for us to be loading data into other systems, as well as do kind of offline large queries, analytics, like data science analytics, offline using Iceberg.
Okay, and we have more questions there. Ryan's helping with a lot of questions. Let me just read through if there's anything that hasn't been answered yet. It's asking about join is relatively memory intensive. How big are your nodes to handle? And is the automatic scaling of CelerData being able to handle the burst, in the query?
So we use the shared nothing architecture. So that has physical disk on the backend nodes. That doesn't yet have auto scaling. There is a shared data architecture for StarRocks. It wasn't quite available at the time that we started this migration. It's definitely something that we're looking into, where the data is stored in S3 or another cloud storage, which allows you to do that auto scaling. So we don't use auto scaling right now because we're on a different architecture, but that's definitely an area of interest for us in the future.
Thank you. Yeah, the next question is the same thing: replicated cluster or shared data cluster? Yeah, you guys use the
so we have one shared cluster for all of our data with multiple replicas of the data. And then it, evenly distributed across the cluster for the best performance and really being able to utilize all of that CPU for every single query as possible.
Okay. How does collocated data work with shared data cluster? Is there a performance degradation because data is in S3 here?
Sida, you probably know that better than I do, but I don't think you can actually do co-location in the shared data.
I mean, each shard is assigned to a node. I think that it's in the shared data or in the shared nothing world. I mean, that works the same. Right?
Okay, so
yeah, each one is assigned to. You can still distribute it by on the same key. And
so files on S3 or your cloud storage would be sharded that way.
Cache,
so each node, each node is going to read just the set of data of tables that have that a specific collection of keys. So that's awesome.
Yeah, that's I think how it works. Yeah, I'll probably have to follow you up on that question with more detail. And is there a performance degradation because data is in S3 here? I think yes and no. So S3 is inherently a lot slower, right? The latency is like 100 milliseconds. But we do have a caching framework that's designed for this kind of like customer-facing like workloads, right? So we are able to cache the data on S3 into your local memory and disk. So to speed up that process. So if you're running something like customer-facing, you're always accessing the data has actually that hot and cold kind of property. That's going to work really well. And so you provision enough memory and disk,
So see, I have a follow-up question for you on that. Has CelerData done any look into S3's single AZ buckets that they claim have better performance?
Oh, the Express One thing?
Yeah.
Oh, that thing? Yeah, we tested it. And we actually have a blog out there, I think, that showcases the result. Yeah, it's pretty fast. It's like GP2 EBS kind of fast. Yeah. So we have tested it. And do you have exact count distinct use case on high cardinality string column?
Sorry, can you repeat that, Sida?
Do you have exact count distinct use cases on high cardinality string columns?
No, we don't do a lot of those types of particular queries.
Okay.
Unfortunately, I can't comment on the performance of those.
That makes sense. Quick question for join key collocated in the same node. I may have missed the context here. Are those nodes both compute and storage nodes? I mean, the Postgres where compute and storage are coupled.
So the backend nodes in a StarRocks cluster are a combination of local disk and compute in the shared the shared nothing architecture.
Yes.
So you're getting, you have local disk, so you're getting the fastest, in theory, the fastest disk performance that you can get, and the lowest latency on disk reads that you can get.
That makes sense. Yeah, there is a shared nothing. Basically, B does both of the execution and the storage, and there's a shared data. It's called CN compute nodes, and it only does execution and reads data off S3, right, where the data is persisted as StarRocks files.
And we're definitely looking into experimenting with that in the future, and seeing what the benefits of each one are. It's a very exciting technology.
Yeah,
and that power to do both, right? The power to have one engine that has both of those architectures, and lets you make certain trade-offs without changing your technology.
Yeah, and you can query Iceberg at the same time, right?
Oh yeah, in both,
formats and lakehouse,
infinite possibilities. It's great.
Yeah, I think that's all of the questions that we have for today. Thank you so much, Nick, for this amazing talk. I definitely learned a lot from it. I believe the audience as well. So if I have any follow-up question, please don't hesitate to ask them on Slack. And we're gonna have the recording out soon in a few days. Okay. Thank you everybody for joining. Thank you. It was a lot of fun.
Yeah, thank you, Sida, and thank you everyone for coming to my talk.
Thank you.
Great hearing all your questions.
Thank you. Appreciate that. Thank you. Bye. See you next time.